Hello. Artificial intelligence towards materials maps. This work was done together with Claudio Draxel, Luca Chiringelli, and several others who will be noted on the respective slides. The challenges in big data and analytics and material science are sketched here. Considering all the atoms from the periodic table and all the possible structures, the number of possible materials is practically infinite. Thus, there is no way to cover this huge structural and chemical compound space directly and completely with high throughput screening. We will get important information and necessary information by high throughput experiments and calculations, but this will never cover everything. The daunting challenge for material science is that the interesting materials are very rare. The interesting materials, that is materials with a high performance function, are statistically exceptional. A route towards solution is to create maps of the material's properties and functions. These maps rely on the knowledge of the appropriate coordinates, here called descriptor D1 and descriptor D2. Only if we have found the appropriate descriptors, we may discover such a map where in relative small areas there are the materials that are good superconductors, and in other areas there are materials for photovoltaics and so on. In my talk, I will show how this coordinate system, that is the two or more descriptors, can be found by artificial intelligence. Pattern discovery for uncovering physical characterizations. In this tutorial picture, I plot the materials property Y as a function of the materials descriptor D. Machine learning employs a global model. That is, it uses a single model to describe the whole population. It therefore minimizes the overall prediction error using regularization. This means that we disregard local details on purpose. Thus, with these gray data points and using a global model, here a linear regression, the best fit looks like this. The method that I like to advocate is subgroup discovery, and I'd like to acknowledge Mario Bolay and Gilles Freken, who have introduced us to the concept. The point is that there may well be more information behind these points. The points may be red and blue, but this information is not known to us. Nevertheless, the correct, meaningful fit would be this. These are two distinct subgroups defined by the condition sigma 1 and sigma 2. This is the science we like to recover in the data, and with this, we also get a better and meaningful description. In this case, even orthogonal to the global model. As I said, we may not know that the data points are red and blue, but still we hope that AI can help us to find out. Here is another tutorial picture for the same problem. These are about 1000 data points, and now we have two descriptors, x1 and x2, and we have a property y that can have two values, circle and square. How can we find structure in the data? If you look at it, you may be able to identify something immediately. Here is a region where we have only squares. Obviously, we want that such identification is achieved automatically. Let me emphasize that this pattern is only visible if we plot the data as a function of these descriptors x1 and x2. If we would use other descriptors, this structure may not show up. Thus, we also need that the coordinates, that is the descriptors, are found automatically. This is what subgroup discovery is doing, finding the coordinates and finding the patterns. In more mathematical words, we like to find Boolean conditions, also called selectors, which may be combined into a conjunction. And we like to maximize a quality function which addresses our target property. This quality function is predefined, but the Boolean conditions and the coordinate systems are not. They need to be identified by the subgroup discovery procedure. For this tutorial figure, one conjunction could be like this. x1 should be between 0.25 and 0.75, and x2 should be bigger than 0.9. This conjunction defines the just mentioned group, which is 100% pure, all squares. And here is another group that contains only circles. And here is one that is not pure, but dominated by squares. So this is the type of identification we like to achieve. Let me mention one example of a quality function. but there are many others. For example, the example here is the information entropy. P is a probability to find a certain value, for example, circles in the subgroup. Simply speaking, this is the percentage of circles compared to all data points in the subgroup. And this probability is multiplied with the logarithm of the same probability. When the subgroup is pure, 100% circles or 0% circles, the entropy is 0. This is what we like to achieve, as good as possible, finding a subgroup which is as pure as possible, maximize the negative entropy. Let me demonstrate how subgroup discovery works with a specific example, turning greenhouse gases into useful chemicals and fuels. This work was done together with these gentlemen. CO2 is typically considered a bad gas. However, I'm convinced that at some point CO2 may well be an important raw material for creating fuels and valuable chemicals, as indicated here. This is all possible already today, but the process is very inefficient. We need a better catalyst, and I'd like to show how subgroup discovery may accelerate the process to find one. We have looked into metal oxides because oxides are typically cheap and stable. We looked at stoichiometries noted here, and we considered materials like manganese, calcium, strontium, barium, aluminum, and so on and so on. These are many different materials. Catalysis happens at surfaces, and so we also considered various surfaces of all these materials. How can we find such surfaces? Or how can we find which surface and which material is a potentially good catalyst, and therefore should be considered or studied in more detail? We did not calculate the full catalytic process. We had done such studies in the past and learned that the many aspects that rule heterogeneous catalysis are too intricate and that a full theoretical description does not make much sense. Alternatively, we ask which material activates CO2. This idea is well established. CO2 is bad for the atmosphere because it's very stable. A stable molecule needs to get activated, and only then it will undergo a chemical reaction. In the gas phase, this is achieved by charging the molecule. This weakens the CO bonds, and it is visible by a change of geometry from linear to bent. This bent molecule will then happily do a chemical reaction. So the idea in surface science was that we need materials where the adsorbed CO2 molecule looks as shown here. As I said, this was and is understood to be the first but necessary step for the catalytic conversion. This was the idea. Surfaces which promote such a geometry may be a good catalyst. Other surfaces don't need to be considered. Now, we looked at activation with less prejudice and considered also other scenarios. We considered 5 different scenarios that may be indicators of weakening the chemical bond. An alternative idea is, for example, that the bond length is increased. Clearly another indicator of weakening the bond. There are other possibilities, but because of time, I will only concentrate on these 2 ideas here, bond angle and bond length. In the publication, you find more actual subgroup discovery then goes as follows. We first have to define the target property. So let's say we choose number 1, bond angle. We like to find subgroup that promotes a small angle. Then we have to define the quality function that should be maximized. And here you see what we have done. There is a cutoff telling that we only look at systems, materials that when you absorb CO2 will result in an angle smaller than 132 degrees. We also want that the subgroup is not too small. The size of the subgroup should be as big as possible under the other constraints. We then have the condition that OCO angle should be different to the gas phase angle. And we have a condition which takes care of the Sabatier principle, namely that molecules should bind to the surface not too weakly and not too strongly. If the binding would be weak, the molecule would not stay there. If the binding would be too strong, the molecule would not do another chemical reaction. Here we actually are using the information gain that I had mentioned earlier. This is the quality function. But now we have to find the coordinate system that is the descriptive parameters that describe and identify the subgroup. We used 46 different potential features, such as free atom properties and properties of surfaces. hoping that at the end our scheme will select 4 or 5 of these many features as being relevant for the description of the relevant materials. In simple words, we use essentially everything that we felt may be relevant, admitting that we don't really know what parameter at the end will win for describing the activation of CO2. The answer, which of the 46 features are actually important and what should be their range, is then determined by the mentioned quality function and a Monte Carlo scheme. Here is the result, displayed in terms of the OCO angle and the CO bond length. Thus the coordinates here are the two quantities we are interested in, but what are the physical parameters, the materials genes that identify the subgroup? This comes in a moment. The blue subgroup is the small angle subgroup, and the green subgroup, the large CO bond length subgroup. The descriptive parameters that identify the materials of the two subgroups are here. Thus, for the small angle, blue subgroup, we have the change at the surface oxygen atom of the clean surface, the energy of the maximum of the P density of states of the surface oxygen atom, the kurtosis of the O to P density of states of the oxygen, of the surface oxygen atom, the maximum value of the two ionization potentials of the two free metal atoms, the minimum value of the two radii of the HOMO radial wave functions of the two free metal atoms. As you see, these are free atom and clean surface quantities, and they characterize the catalyst material. These parameters are also called materials genes, as they correlate with different mechanisms that trigger, but maybe just facilitate, or that hinder the different processes which play together, very much as genes in biology. And for the green subgroup, we have other descriptive parameters or genes, as noted here. Please check our publication preprint for more information. In the coordinate system of this plot, the blue and the green dots don't look like a group. They are different, these two groups, but they are really scattered around. Obviously, the group character is defined by means of these parameters here and here, not by the coordinates of the plot. As I said earlier, evaluating the efficiency of a realistic catalyst numerically and reliably is not really possible or does not make much sense. Too many different processes are playing together. Thus, after all the theoretical analysis, we will now use experimental information. There isn't much experimental information, but there's 7 different materials and which have been studied in catalysis. Most materials with good catalytic performance belong indeed to these two subgroups, blue and green. Thus, we conclude that searching for a good catalyst, one should look at the region in material space that is defined by these two subgroups, and one can ignore the other materials. A critical component of the described work and our vision is an efficient research data infrastructure. You need data from your own calculations, but also from other people's work. For Nomad, this is sketched here. The entrance level for new data is the Nomad repository. Here we accept data from 40 different software packages in the field of first principles, electronic structure theory, molecular dynamics, and increasingly also from force field codes. We request the full input and output files, and we ask for the data in a way they are produced by the employed software. Thus, the user does not have to do any work. We will then parse, convert, and normalize the data, and these converted data are stored in the Nomad archive. Only together, repository and archive are fully fair. By the way, if a software is not yet served, we are happy to write parsers and converters together with the developers of the not yet served software. However, all bigger and all widely used codes are there already. Data in the repository and archive are stored for at least 10 years, After the upload, they can get a DOI, so they are citable. More information can be found on the Nomad website. There is a lot of information in the archive, and one can look at it via the Nomad encyclopedia, or one can do data analytics by using the Nomad Artificial Intelligence Toolkit. Nomad is the biggest data store in computational material science, and we are in close contact with all bigger databases in the US, AFlow, OQMD, Materials Project, and more. There is an automatic synchronization that fetches their data, stores their raw data at Nomad, and then converts them into the archive. About 70% of all the data in Nomad come in fact from these databases. The other 30% come from various other groups and individual researchers. Our definition of fair is actually findable and AI ready, which is even more demanding than the original definition. So far, Nomad is focusing on computational material science, but this is changing. We just started with the integration of materials synthesis, experiment, theory and computations, and applications into Nomad or its successor. Let me say some words about synthesis. Some of our leading experts are shown here. In very simple words, the issue is make synthesis reproducible. If you think scientific research should be reproducible in general, the sad truth is that this is often not the case, and this is a big problem in material synthesis, which often is more an art than clean science. This is what we like to change. The first goals are establish metadata standards, ontologies, and tools, harmonize metadata of synthesis and experimental characterization, create what we call handbooks on what data are needed for a sound sample characterization. This concept is also called clean data, and I will get back to it in 2 minutes. Another team is looking into various experimental methods used in material science. The people are shown here, and the first goals are implement an efficient and persistent linkage of data types by means of LIMS and ELN solutions, but keep this flexible. Lead by example, not by rules. Test and demonstrate the functionality of the data infrastructure and identify weaknesses to be improved. Make sure that all of this helps the active researchers and does not create unnecessary burden. Let me finish with one more example from Catalysis to elucidate the concept of what we call clean data. Clean experiments and artificial intelligence. Here is what and how we perform what we call a clean experiment, an experiment that provides data that are then useful for AI analysis. In heterogeneous catalysis, one starts with the synthesis of the catalyst material, and this material is then put into a test catalytic reactor. The first effect there is that the material will change. Catalysis is a dynamic process with changing structure under reactive or reaction conditions. And then one measures the reactivity and the cell activity. Clearly, we need materials information about the fresh catalyst and about the modified activated material. The experimental methods look at the crystal structure, at the mesoscopic assembly, at bulk and surface properties, at the chemical behavior, conductivity, and so on. This is a lot of work that needs to be done in these studies, and therefore this is typically not done in such detail. However, it is important because it provides us with the needed characterization of the material, of the fresh and the active samples. The samples, by the way, and then also tagged by a QR code. Using well-characterized data of vanadium-based catalysts, clean data, and offering billions of candidate descriptors, we were then able to identify the most relevant two-dimensional descriptor, 2 out of billions of possibilities. This is done by our AI method called CISO, Sure Independent Screening and Sparsifying Operator. The methods will be described later in the same session at 4 p.m. by Luca Chiringelli. A key issue in catalysis is selectivity, because typically several reactions compete, but only one reaction, that is one product, is of interest. Here it is the conversion of propane into acrylic acid. This figure shows the AI determined selectivity map for the conversion of propane into acrylic acid. Dark blue is high selectivity. The descriptor D1 at the y-axis identifies the material, and the x-axis shows the temperature. The straight lines correspond to the few catalysts where we have experimental information. There's very few experimental data, just 9 different materials, but this is the typical situation. Few data, but an immensity of possible physicochemical effects. The CISO method then gives us a descriptor D1, which tells us really what one should do to optimize the material in order to find a better performance, high selectivity catalyst. As you can see, the descriptor is rather complex, and it depends on 7 different quantities. The dashed green line here on the plot is in fact a prediction. Everything else is really data. This dashed line is a prediction where the mesoscopic porosity was increased. I'm running out of time to explain this in more detail, but would be happy to get back to it in the discussion, or I suggest that you look at the preprint that you can find on our webpage. Let me come to the conclusion. A fair research data infrastructure is what we need, and what will enable a new level of materials research. This is also called the 4th paradigm of data-intensive science. Our forward-looking interpretation of the acronym FAIR is that research data should be findable and AI-ready. This contains and extends the standard definition of FAIR. Integrating synthesis, experiment theory, computations, and applications will further the basic sciences in materials research. And let me add that this will also reach out to chemistry, engineering, industry, and society. Good progress has been made in computational material science already, very much demonstrated by AFLOW, Materials Project, OQMD, and by others, including us. Challenges in material synthesis and experiment are much more difficult. We are on the way, and first promising, impressive steps have been made already. Now, if people listening to this talk worry and or work on the same issues, it would be great if you would get in contact with us. We should work together because we like to build one common research data infrastructure, and we need to coordinate our metadata activities. Thank you very much for your attention.